Hi. So I'd like to continue on with our discussion of Chapter 4 and discuss Carnot engines. Yet again, my resources are Schroeder's Thermal Physics textbook and some resources from Thompson Higher Education. So first, let me review what reversible and irreversible processes are. So a reversible process is one in which every point along some path is in an equilibrium state, and one for which the system can be returned to its initial state along that same path. An irreversible process doesn't meet these requirements. Now, it's true that all natural processes are known to be irreversible. Reversible processes are really an idealization because nothing's perfect. There's always going to be friction, there's always going to be dissipation of energy and loss. But some real processes can be good approximations to the truth. Now, it's also true that unfortunately, what that usually means is that the process is very slow, but we'll get to that more in a second. Okay, so if you want to keep something in equilibrium state pretty much every point along the way, then you have to have the process be slow so that at every step it can equilibrate again. So you make a tiny change, you wait, you make a tiny change, you wait, you make a tiny change, you wait. So that's why the processes are slow, okay? And a general characteristic of reversible processes is that there's no dissipative effects that convert mechanical energy to internal energy like friction or turbulence. And of course, that's really hard to achieve in real life. So all reversible processes are actually idealizations, and all real processes on Earth are irreversible. But they do give us a goal to shoot for in what could theoretically be achieved, and that's where the Carnot engine comes in. Now, Carnot lived from 1796 to 1832, so he had kind of a short lifespan, but he managed to do quite a lot with the time that he had. He was a French engineer, and he was the first to show that there was a quantitative relationship between work and heat. His publication, Reflections on the Motive Power of Heat, reviewed the industrial, political, and economic importance of the steam engine. So, a Carnot engine is a theoretical engine that was developed by Carnot. And it's a heat engine that operates in an ideal reversible cycle that we now call the Carnot cycle in his honor. And it operates between two reservoirs at given temperatures, and it's the most efficient engine possible. Since it's a theoretical construct, it's what all other engines shoot for. And it sets an upper limit on the efficiencies of all other engines. Now, no real heat engine that operates between two energy reservoirs can be more efficient than a Carnot engine operating between those same two reservoirs. In other words, all real engines are less efficient than Carnot engines because they're not reversible. So the efficiency of a real engine is also going to be further reduced, even though you can't have a reversible cycle in a real engine. You're going to have it even reduced from that because of friction, energy losses, turbulence, things like that. So we're going to talk about what the Carnot cycle processes are. But to sum up really quickly, it contains two isothermal processes and two adiabatic processes. So let's go through them step by step. We're going to call the first step in the Carnot cycle moving from A to B. And this will make more sense in just a second when I show you the PV diagram. Now, A to B is an isothermal expansion. What happens is you place your gas, which is the material that it's operating in a cycle through, you place your gas in contact with a high temperature reservoir, and the reservoir is at some temperature T sub H. At this point, the gas absorbs heat, which we'll call Q sub H, and the gas does work in raising that piston, because when it's in contact with a hot reservoir, hot gases expand, and so it's going to raise the piston because of that expansion. Now, in step B to C, you have an adiabatic expansion. Basically what happens there is that you place an insulator in contact with the base so that it can't draw any more heat energy from the hot reservoir, but the gas continues to expand just a little bit. No heat is going to enter or leave the system at this point. The temperature starts to fall from TH to TC, and the gas continues to do work, B sub C. The gas is then placed in contact with a cold temperature reservoir, and then you have an isothermal compression. The gas expels energy, Q sub C, and work CD is done on the gas. And then finally, D to A, taking you back to your starting point, that's an adiabatic compression. The gas is again placed against a thermally non-conducting wall, so no heat's exchanged with the surroundings, and the temperature of the gas increases from Tc to Th. The work is done on the gas, work dA. Now if we put all of this stuff that I just described into a PV diagram, then you can see the two isothermal steps there. You have the isotherms at T sub H with the hot reservoir and T sub C with the cold reservoir. So you can see that A to B follows that isotherm T to H. Then remember that adiabats are steeper than isotherms. So when you go from B to C, you have the adiabatic expansion B to C. And then you have the isothermal compression, so it follows the isotherm T sub C at the colder temperature. And then yet again, adiabats steeper than isotherms for the compression that goes from D to A. Okay? Now because it's a cyclic process, of course, the change in the internal energy for the cycle is going to be equal to 0. And so that means that the net heat is going to equal to the magnitude of the net work, right? Also remember that for cyclic processes on PV diagrams, the work done by the engine is going to be the area enclosed by that curve. So it'll be in this kind of beige shaded region right here that gives you the work of the engine. All right? That net work is going to equal to QH minus QC because of energy conservation. Now, Carnot engines are a great theoretical construct and they set upper limits on efficiencies, but they're really not practical. And that's because the isothermal steps would be really rate limiting. Remember, adiabatic things can be really fast, but isothermal processes are generally much slower. And so what that would mean is that if you took it through a cycle, it would take minutes or hours to go through instead of a fraction of a second. And also remember that when we're talking about engines, it's really power that we want, work divided by the time. That's what's important, and it's not just the work. Now, Carnot showed that the efficiency of the engine for this process would depend upon the temperatures of the reservoirs. And so we still have the two equations for efficiency that worked for all engines. The efficiency is equal to the work of the engine divided by Q sub H, which is equal to 1 minus Q sub C over Q sub H, absolute values. But for the Carnot engine, you can also add on an extra equation that the efficiency would equal to 1 minus Tc divided by Th, where Tc and Th are the temperatures of the cold and the hot reservoir in Kelvin. Okay? All the Carnot engines operating between the same two temperatures are going to have the same efficiencies. So it's really for a Carnot engine just about the temperatures of the cold and the hot reservoir. Now looking at this equation, you can see that the efficiency would be 0 only if the temperatures are the same for the cold and the hot reservoir. Of course that doesn't make any sense, so there you have it. The efficiency would be 100% only at absolute 0, so you can see how unachievable that would be. The efficiency is going to be increased as Tc is lowered and Th is raised. Now, in practical cases, Tc is going to be near room temperature, roughly 300 Kelvin. And what you have to do to increase the efficiency is to increase the temperature of the hot reservoir. Now, why is this equation true, this 1 minus Tc divided by Th? Okay, well remember that for quasi-static processes, the change in the entropy would be equal to Q divided by T. So what that means is that the entropy dumped to the cold reservoir, delta S sub C, is going to equal to QC over TC. And that has to be greater than or equal to QH divided by TH, which is the entropy that's drawn from the hot reservoir. Okay? So that's the second law of thermodynamics. Now, if you rearrange that equation, then you get Q sub C over QH is greater than or equal to T sub C over TH. Just doing a little cross multiplication here with your QC, TC, QH, TH terms, right? So you can see then that if you plug in TC over TH for QC over QH, then what you get is an inequality. The efficiency is equal to 1 minus QC over QH, which is less than or equal to 1 minus TC for T over TH. And so this is the Carnot efficiency that places that upper limit. The efficiency will always be less than or equal to that. Okay? It'll be equal only for Carnot engines, and it'll be less for all real engines. So the explanation for this in words is that it's an upper limit because in this engine, the entropy gained from the hot reservoir would have to be the same as the entropy dumped to the cold reservoir. And since in all real engines entropy increases, this is just an impossible dream. Alright, now you can also have Carnot heat pumps and Carnot refrigerators. Theoretically, a Carnot cycle heat engine could run reverse, and if it did, then this would be the most effective heat pump available, and it would give the maximum possible coefficient of performances for a given combination of hot and cold reservoirs. But, just like the Carnot engine, it's not practical because of the power requirements. Remember that time is very important here when you're talking about your heat pumps. So it's heat extracted over time. So a Carnot pump would be very slow. Now, Carnot heat pump coefficient of performance equations. Basically, we have the same kind of thing that we had before. In cooling mode, for example, like inside of a refrigerator where you want to make the inside of the cold box colder, your entropy delta SH sucked from the hot reservoir would be equal to, quasi-static equation here, QH divided by TH, which would have to be greater than or equal to QC over TC, right? Rearranging those equations, you have QH over QC would be greater than or equal to TH over TC. Now the coefficient of performance in cooling mode would be QC over W, or QC over QH minus QC, using energy conservation equations relating the work to the heat extracted. So if you rearrange that equation and divide the top and the bottom of that fraction by Q sub C, then you end up with 1 over QH over QC minus 1. Or if you want to write that in terms of the ratio there, QH over QC, that would place the TH over TC there, and then you have your less than or equal to sign. And you end up then, when you multiply through by TC, with an equation TC over TH minus TC. And that would be the coefficient of performance in cooling mode. And you could do the same thing in heating mode, right? And the coefficient of performance in heating mode, the steps would be very similar for the mathematics, and you end up with the coefficient of performance in heating mode is TH over TH minus TC. So that's the theoretical limit for Carnot heat pumps and air conditioners. Okay, so let's estimate the max possible coefficient of performance for a household air conditioner using reasonable values for the reservoir temperatures. Alright, well, here we have the coefficient of performance for an air conditioner, for a Carnot, is TC over TH minus TC. Now let's put reasonable temperatures in there. A goal for inside the home might be room temperature, which I think of as roughly 20 degrees Celsius. If you exchange that to Kelvin, it's 293 Kelvin. Now on a hot day when you'd be running your air conditioner, it might be like 35 degrees Celsius outside. That's 308 Kelvin. So if you plug that into the equation for the coefficient of performance, you have 293 divided by 308 minus 293, and you get about 20. Coefficient of performance about 20. Now this is a theoretical limit. Real air conditioners might achieve half that value if they're lucky. Let me do another example problem for you with a Carnot heat engine. In this example problem, you have an electric power plant that would make use of the temperature gradient of the ocean. And the system would be to operate between 20 degrees C, which is the surface water temp, and the much colder water temperature at a depth of 1 kilometer of 5 degrees C. So what would be the max efficiency of such a system? And if the electric power output of the plant were designed to be 75 megawatts, then how much energy would be taken in from the warm reservoir per hour? And then based upon the efficiency that you found in part A, explain whether or not you think it would be worthwhile to do this system. Okay, so using our theoretical equations for Carnot heat engines, the efficiency is 1 minus Tc over Th for the theoretical limit. Now, based upon the temperatures given in the problem, 20C and 5C, that would be converted to Kelvin. You always have to convert to Kelvin. And so then you have 1 minus 278 divided by 293. That gives 0.051, or a 5.1% efficiency. Now, that efficiency would also equal to the work put out divided by the heat energy extracted, or W divided by Q sub H. However, the problem gives us power, not energy. And so remember that that energy is that power is energy divided by time. And so I could just divide the top and the bottom of that fraction by time, and you'd get the efficiency is equal to the work divided by time divided by QH over time. Now, we already solved for what that efficiency is. It's 0.051. So plugging in what the necessary power output is for work over time, it's 75 megawatts. And then we could find out what the power extracted from the hot reservoir would be. So if you take 75 megawatts and divide it by 0.051, then you get 1470.6 megawatts. And that would be the power that you would need to extract from the hot reservoir. Now, we want how much energy is extracted on a per hour basis. So to get energy, you'd multiply power by time. Now the time is 3,600 seconds in 1 hour, and so pH times T would be 1470.6 times 10 to the 6th watts, or megawatts, times 3,600 seconds, and that would give you 5.3 times 10 to the 12th joules. Okay? So that's how much energy you'd have to extract from that hot reservoir each hour. Now part C is a little bit more of an opinion here. My opinion would be that since 5.1% is the theoretical maximum of the power plant, the real efficiency would be much lower, maybe half that or a third of that. So it really doesn't seem worth it to me for such a low efficiency to put all that money into constructing the power plant, not to mention maintaining it and running it, especially when there's a lot more efficient options for renewable energies that use the oceans. You could put in, for example, something that would cause the wave motion of the ocean to turn turbines, or you could put some wind farms offshore that utilize the ocean winds, and that would be more efficient. Okay? So that sums it up for me for Carnot heat engines and heat pumps. See you next time.